You know what scares NASA more than failed launches? Successfully getting astronauts to Mars and watching them deteriorate so badly they can't complete the mission. There's one danger lurking on this journey that's far more terrifying than rocket explosions or equipment failures. It's invisible, it's relentless, and it's already changing the astronauts who venture beyond Earth's protective embrace. If you're as fascinated by space exploration as I am, hit that subscribe button and give this video a like. Now let's get started. So what keeps NASA scientists awake at night as they plan humanity's first crewed mission to the Red Planet? The answer is radiation. But not just any radiation. We're talking about a cosmic onslaught that makes a chest X-ray look like a gentle breeze. And the truth is, NASA knows exactly how devastating this threat really is. Here's what most people don't understand. When you're on Earth right now, you're protected. Above your head there's an invisible shield, Earth's magnetosphere. This magnetic bubble extends thousands of miles into space, deflecting charged particles from the sun and cosmic rays from distant exploded stars. It's been protecting life on our planet for billions of years. Without it, Earth would look more like Mars, a barren, radiation-scorched desert. But when astronauts leave Earth orbit, that protection vanishes. Let me put this in perspective. Astronauts on the International Space Station receive about 50 to 200 millisieverts of radiation per year. That's roughly equivalent to getting 10 full-body CT scans. Sounds like a lot, right? Well, the space station is still partially protected by Earth's magnetic field. It orbits just 250 miles above the surface, still within the outer edges of our planetary shield. Mars is a different story entirely. A mission to the Red Planet will take anywhere from 6 to 9 months each way. That's over a year and a half in deep space, with potentially another year and a half on the Martian surface. During that time, astronauts will be exposed to radiation levels that are completely unprecedented in human spaceflight. Recent data from NASA's Artemis 1 mission, which flew around the Moon in 2022, gave us our most accurate measurements yet. The findings were sobering. Instruments aboard the uncrewed Orion spacecraft measured radiation doses that would expose astronauts to approximately 60 millisieverts during a 3-week lunar mission. Now multiply that exposure over the 3-year duration of a Mars mission. We're looking at doses approaching or exceeding 1 sievert. That's 1,000 millisieverts. To put that number in context, radiation workers on Earth are limited to 50 millisieverts per year. A dose of 1 sievert significantly increases your lifetime risk of cancer. But cancer isn't even the most immediate concern for Mars-bound astronauts. The real nightmare is what happens to the brain. Scientists at NASA and research institutions around the world have been studying this for years. They've exposed mice to the same types of cosmic radiation that astronauts would encounter in deep space. The results are deeply unsettling. These particles, especially heavy ions like iron nuclei traveling at nearly the speed of light, don't just pass through tissue. They tear through it like microscopic bullets, leaving trails of destroyed cells and broken DNA in their wake. When these particles hit the brain, they damage neurons and disrupt the delicate networks that control everything from memory to decision-making. In animal studies, researchers observed increased anxiety, impaired memory, and reduced cognitive function. Some mice even showed signs of early Alzheimer's-like symptoms. Imagine experiencing that while you're millions of miles from Earth, responsible for operating complex equipment and making split-second decisions that could mean life or death for your crew. Here's where it gets even more concerning. Unlike most radiation on Earth, which comes in the form of X-rays or gamma rays, cosmic radiation includes heavy charged particles. These are the nuclei of atoms, stripped of their electrons and accelerated to incredible speeds by supernova explosions and other violent cosmic events. When they strike human tissue, they don't just damage the cells they hit directly. They create cascades of secondary particles, spreading the destruction like shrapnel from an explosion. Your body has mechanisms to repair DNA damage. Evolution equipped us with sophisticated molecular machinery that can fix broken genetic code. But cosmic radiation is different. It causes complex DNA damage, multiple breaks in close proximity that our repair systems struggle to handle correctly. When repairs go wrong, cells can become cancerous or simply die. In the brain, where neurons don't regenerate easily, this is catastrophic. NASA calls this the risk of acute and late central nervous system effects from radiation exposure. In plain English, it means astronauts could experience immediate cognitive problems during the mission, along with long-term neurological issues that might not appear until years after they return home. But wait, you might be thinking, can't we just shield the spacecraft with thick walls? Add more metal, more insulation, more protection? This is where the problem gets truly diabolical. Traditional shielding doesn't work the way you'd expect in space. When high-energy particles slam into metal, they sometimes create secondary radiation that's even more dangerous than the original particle. It's called nuclear fragmentation. A heavy cosmic ray hits an aluminum wall, and suddenly you've got a shower of neutrons and lighter particles spraying into the spacecraft. You're essentially creating radiation inside your own ship. Engineers have explored countless solutions. Some propose using water or polyethylene, materials rich in hydrogen atoms that are better at absorbing radiation without creating as much secondary particle spray. Others suggest surrounding sleeping quarters with water tanks or food supplies to provide at least some protection during rest periods. But there's a fundamental problem. Every kilogram of shielding material is a kilogram that needs to be launched from Earth, and launch costs are astronomical. Literally. To provide truly effective radiation shielding for a Mars mission, you'd need walls several meters thick. The mass would be enormous, requiring multiple heavy lift rocket launches just to get the shielding into orbit. We're talking billions of additional dollars and years of extra preparation. Even then, you're only reducing the radiation exposure, not eliminating it. So here we stand, at the threshold of interplanetary exploration, facing a danger that we can measure and understand but cannot fully defeat with current technology. NASA isn't sitting idle, though. Scientists and engineers are developing innovative approaches. Some involve faster propulsion systems that would cut travel time in half, reducing exposure duration. Others focus on biomedical countermeasures, drugs or therapies that might help the body repair radiation damage more effectively. There's even research into artificial magnetic fields that could surround a spacecraft, creating a miniature magnetosphere like Earth's. But as of 2026, none of these solutions are ready for prime time. And that means the first humans to journey to Mars will be taking a calculated risk that would make most of us think twice. The radiation story gets even more complex when we consider what's actually bombarding spacecraft in deep space. There are two main sources, and understanding the difference between them is crucial to grasping why this problem is so difficult to solve. First, there's solar radiation. Our star, that brilliant ball of plasma 93 million miles away, is constantly ejecting charged particles into space. This stream of protons and electrons is called the solar wind, and it flows outward from the Sun at speeds of about 1 million miles per hour. Under normal circumstances, it's dangerous, but manageable. Spacecraft can be designed with this baseline level in mind, but the Sun isn't always calm. Roughly every 11 years, our star goes through a cycle of increased activity. During solar maximum, the Sun's surface becomes covered with dark sunspots, regions of intense magnetic activity. These twisted magnetic field lines can suddenly snap and reconnect, releasing enormous amounts of energy in events called solar flares and coronal mass ejections. When a major solar eruption occurs, it launches billions of tons of plasma into space. If one of these events happens while astronauts are traveling to Mars, they could receive a lethal dose of radiation in a matter of hours. We're talking about enough exposure to cause acute radiation sickness, nausea, vomiting, hemorrhaging, and potentially death. The last truly massive solar storm hit Earth in 1859. It's called the Carrington event, named after the British astronomer who observed it. Telegraph systems around the world sparked and caught fire. Auroras were visible as far south as the Caribbean. If a storm of that magnitude struck a spacecraft today, with astronauts unprotected in deep space, the consequences would be catastrophic. NASA monitors the Sun constantly, using satellites like the Solar Dynamics Observatory and stereo spacecraft positioned at different points around our star. These early warning systems can detect solar eruptions and provide some advance notice. But here's the problem. Light travels from the Sun to Earth in about 8 minutes. The fastest solar particles arrive in as little as 15 to 30 minutes. That's not much time to seek shelter, especially when your spacecraft might not have a dedicated storm shelter with adequate shielding. Some mission designs include a small heavily shielded compartment where astronauts can huddle during solar storms. Think of it as a panic room in space. But spending days or weeks crammed into a tiny box with your crewmates, waiting for the radiation storm to pass, adds another layer of psychological stress to an already challenging situation. And solar radiation isn't even the worst part. There's a second source of radiation in space that's far more insidious, because it's constant, unpredictable, and essentially unstoppable with current technology. Galactic cosmic rays. These are particles accelerated to near-light speeds by some of the most violent events in the universe. When massive stars explode as supernovae, they create shock waves that act like cosmic particle accelerators, whipping atomic nuclei to incredible velocities. These particles then wander through the galaxy for millions of years, spreading throughout interstellar space. Earth receives galactic cosmic rays from every direction all the time. Right now, as you're watching this video, thousands of these particles are passing through your body every second, but you're protected. Earth's atmosphere and magnetic field stop or deflect the vast majority of them. In space, there's no such protection. What makes galactic cosmic rays particularly nasty is their composition. While solar radiation is mostly protons and electrons, galactic cosmic rays include heavy nuclei: carbon, oxygen, silicon, iron. These massive particles carry tremendous energy and momentum. When they strike living tissue, they don't just knock electrons loose like lighter radiation does. They physically plow through cell structures, ripping apart DNA strands and creating complex, difficult-to-repair damage. The biological effectiveness of radiation is measured using something called relative biological effectiveness, or RBE. X-rays have an RBE of 1. That's the baseline. Galactic cosmic rays, particularly heavy ions, can have RBE values of 20 or higher. That means they're 20 times more damaging per unit of absorbed energy than the radiation you'd receive from a medical X-ray. Think about that for a moment. Every single day in deep space, astronauts would be accumulating damage from particles that are 20 times more biologically destructive than anything most people ever experience on Earth. And this exposure continues relentlessly, 24 hours a day, 7 days a week, for the entire duration of the mission. Scientists call this chronic low-dose exposure, and it's fiendishly difficult to study. We can't exactly send humans into deep space for 3 years just to measure the effects. Instead, researchers rely on animal studies, computer models, and data from astronauts who've spent time on the International Space Station. But those data points only give us partial answers. Here's something fascinating and terrifying. Recent studies using NASA's Mars Curiosity rover measured radiation levels on the Martian surface. The rover has been carrying a radiation detector called the Radiation Assessment Detector, or RAD, since it landed in 2012. After years of continuous monitoring, scientists calculated that astronauts on Mars would receive about 24 to 30 millisieverts per month from galactic cosmic rays alone. Over an 18-month surface stay, that adds up to 432 to 540 millisieverts, approaching the career limit NASA currently sets for astronauts. And that doesn't even include the radiation exposure during the 9-month journey there and 9-month journey back. Let's do some quick math. Transit to Mars, approximately 300 millisieverts. 18 months on the surface, around 500 millisieverts. Transit home, another 300 millisieverts. Total mission exposure, approximately 1,100 millisieverts, or 1.1 sieverts. That's more than 20 times the annual dose limit for radiation workers on Earth, accumulated over less than 3 years. NASA's current lifetime exposure limits for astronauts are designed to keep their increased cancer risk below 3%. These limits vary by age and gender, but they generally range from 600 to 1,200 millisieverts over an entire career. A single Mars mission could potentially exceed that lifetime limit. Speaking of our first Mars explorers, if you're wondering what other permanent challenges await those brave pioneers, I actually created an entire video exploring why the first humans on Mars will be trapped there forever. The physics and biology behind that are absolutely fascinating, and it connects directly to what we're discussing here about radiation. The video is pinned in the comments and on the card above. Now you might wonder why NASA would even consider sending humans to Mars, given these risks. And that's a fair question. The answer lies in what we hope to gain and how we as a species think about exploration and acceptable risk. Throughout history, explorers have faced mortality rates that would be unthinkable today. Early Antarctic expeditions saw death rates of 50% or higher. The first attempts to summit Mount Everest killed many climbers before Edmund Hillary and Tenzing Norgay succeeded in 1953. When President Kennedy committed America to landing on the moon, NASA estimated they had only a 50-50 chance of success before the end of the 1960s. Astronauts understand the risks. They're test pilots, scientists, and engineers who have spent their entire careers pushing boundaries and accepting calculated dangers. When NASA eventually calls for volunteers for the first Mars mission, there will be no shortage of highly qualified individuals willing to go. But understanding and accepting risk doesn't mean being reckless. NASA has a responsibility to minimize danger wherever possible and to be honest about the threats that remain. The human body is an intricate machine, fine-tuned by billions of years of evolution to thrive in one specific environment: Earth. When you remove that environment, things start to break down in ways that are both predictable and surprising. And when you combine those breakdowns with constant radiation exposure, you get a perfect storm of interconnected health risks that make a Mars mission exponentially more dangerous. Let's talk about what happens to bone. On Earth, gravity is constantly pulling on your skeleton. Every step you take, every time you stand up or lift something, your bones experience stress. And your body responds to that stress by maintaining bone density. Specialized cells called osteoblasts continuously build new bone tissue, while other cells called osteoclasts break down old bone. It's a delicate balance that keeps your skeleton strong. But in the microgravity environment of a spacecraft, that balance collapses. Without gravitational stress, your body decides it doesn't need as much bone anymore. The osteoclasts keep working, breaking down bone tissue, but the osteoblasts slow down dramatically. The result? Astronauts lose bone density at a rate of about 1 to 2% per month in weightlessness. Think about that. After just 6 months, an astronaut could lose 12% of their bone mass in certain areas, particularly in the weight-bearing bones of the hips, spine, and legs. That's equivalent to what a postmenopausal woman might lose in a decade of osteoporosis. After a year and a half in space, some astronauts could experience bone loss comparable to 20 years of aging. Now here's where radiation enters the picture and makes everything worse. Remember those heavy ions we talked about, the ones that tear through tissue like microscopic bullets? They don't just damage DNA and neurons and other soft tissues, they also affect bone cells. Recent studies have shown that radiation exposure can disrupt the signaling pathways that regulate bone formation and breakdown, potentially accelerating bone loss even further. Scientists at NASA have observed that radiation seems to impair the function of osteoblasts, the cells responsible for building new bone. At the same time, it may increase the activity of osteoclasts, the cells that break down bone. This creates a double whammy effect. You're already losing bone because of microgravity, and now radiation is making it even harder for your body to rebuild what's being lost. By the time astronauts arrive on Mars, their bones could be significantly weakened. And Mars gravity, which is only 38% of Earth's, probably isn't strong enough to trigger proper bone rebuilding. So during the 18 months on the surface, astronauts would continue experiencing bone loss, just at a slower rate than in complete weightlessness. The implications are genuinely frightening. Imagine landing on Mars after 9 months in space, stepping out of your spacecraft to explore, and suddenly experiencing a hip fracture just from the impact of walking, or developing stress fractures in your spine from doing routine maintenance tasks. On Earth, these injuries would be serious but manageable. On Mars, they could be catastrophic. But bones aren't the only concern. Let's talk about muscle. Like bone, muscle tissue requires regular stress to maintain its mass and strength. On Earth, you're constantly working against gravity, standing, walking, climbing stairs, lifting objects. All of these activities keep your muscles engaged and functional. In weightlessness, most of that work disappears. Astronauts on the International Space Station exercise for about 2.5 hours every day, using specially designed equipment to maintain muscle mass. Even with this aggressive exercise regimen, they still lose significant muscle, typically around 20 to 30% of their muscle mass over a 6-month mission, particularly in the legs and lower back. Now imagine a Mars mission where resources are limited, space is cramped, and astronauts might not have access to the same exercise equipment available on the space station. Even if they do exercise religiously, the duration of the mission means the cumulative muscle loss would be substantial. And once again, radiation complicates everything. Recent research suggests that cosmic radiation may interfere with muscle regeneration. When you exercise, you create micro-tears in muscle fibers. Your body responds by repairing these tears and building the muscle back stronger. That's how you gain strength. But radiation-induced cellular damage might impair this repair process, making it harder to maintain muscle mass even with consistent exercise. There's also evidence that radiation affects mitochondria, the powerhouses of your cells that generate energy. Damaged mitochondria are less efficient at producing the energy your muscles need to function. This could lead to chronic fatigue, reduced exercise capacity, and a downward spiral where astronauts feel too tired to exercise adequately, leading to even more muscle loss. By the time the crew reaches Mars, they could be significantly weakened, bones brittle, muscles atrophied, energy levels depleted. And they'll need to immediately begin one of the most physically demanding phases of the mission, establishing a habitat, deploying equipment, and beginning exploration activities in an environment where everything is harder than on Earth. Now let's discuss something even more insidious. What's happening to the cardiovascular system? Your heart is a muscle, and like other muscles, it adapts to its environment. On Earth, your heart works hard to pump blood upward against gravity, particularly to your brain. In weightlessness, that workload decreases dramatically. Your heart doesn't need to pump as hard, so it begins to atrophy just like skeletal muscles do. But there's another factor at play. In microgravity, fluids in your body redistribute. Normally, gravity pulls blood and other fluids toward your legs. That's why your feet might swell if you stand for too long. In space, fluids shift upward toward the head and chest. Astronauts often describe feeling congested, like they have a perpetual head cold. Their faces become puffy, and the veins in their necks bulge. This fluid shift has serious consequences. The heart detects increased blood volume in the chest and responds by signaling the kidneys to reduce overall blood volume. Over time, astronauts can lose 10 to 15% of their blood volume. They essentially become mildly anemic. When combined with cardiac muscle atrophy, this means the cardiovascular system becomes less capable of responding to physical demands. If an astronaut needs to do heavy physical work, say performing an emergency repair outside the spacecraft, their weakened heart and reduced blood volume might not be able to deliver adequate oxygen to working muscles. And radiation? It affects the cardiovascular system too, though in more subtle ways that might not become apparent until years after the mission. Studies of atomic bomb survivors and cancer patients who received radiation therapy have shown that radiation exposure increases the risk of cardiovascular disease, heart attacks, strokes, and atherosclerosis. The mechanism isn't fully understood, but it appears that radiation damages the endothelial cells lining blood vessels, leading to inflammation and the formation of arterial plaques. This is a long-term effect that might not manifest during the Mars mission itself, but could significantly shorten the lives of returning astronauts decades later. Let me paint a picture of what all this means in practical terms. Imagine you're an astronaut 9 months into the journey to Mars. You've lost 20% of your bone density. Your muscles have atrophied to the point where tasks that would have been easy on Earth now leave you exhausted. Your heart has weakened and you're mildly anemic. Meanwhile, every single day, cosmic rays have been damaging cells throughout your body, your brain, your organs, your blood vessels. Then something goes wrong. A piece of equipment fails and you need to perform a spacewalk to repair it. You're working in a bulky spacesuit, using tools, exerting yourself physically. Your weakened cardiovascular system struggles to keep up. Your atrophied muscles fatigue quickly. And all of this is happening while you're being bombarded with even more radiation. because you're outside the minimal shielding the spacecraft provides. This is the reality NASA is grappling with. It's not one single danger that makes Mars missions so risky. It's the combination, the synergistic effects of multiple hazards that amplify each other in ways we're only beginning to understand. Scientists call these combined effects multi-system deconditioning. Your body isn't just dealing with radiation, or just dealing with microgravity, or just dealing with isolation. It's dealing with all of them simultaneously, and they interact in complex ways that our current models struggle to predict. There's another critical system in your body that starts failing in the harsh environment of space, and it's one that most people don't think about until something goes terribly wrong. Your immune system. Right now, your body is constantly defending itself against invaders, bacteria, viruses, fungi, and even your own cells when they become cancerous. This defense network is incredibly sophisticated, involving trillions of cells working in coordination to identify threats and neutralize them before they can cause harm. It's the reason you're not constantly sick, despite being surrounded by potentially dangerous microorganisms every single day. But spaceflight disrupts this system in profound ways. Studies of astronauts on the International Space Station have revealed something disturbing. The stress of spaceflight, microgravity, isolation, intense workload, disrupted sleep, causes significant changes in immune function. White blood cell counts become abnormal. The cells that remain don't function as effectively, and certain viruses that have been dormant in astronauts' bodies for years suddenly reactivate. You've probably heard of the Epstein-Barr virus, which causes mononucleosis, the kissing disease many people get in their teens or 20s. Once you're infected, the virus never truly leaves your body. It hides in certain immune cells, kept in check by your immune system. For most people, it stays dormant for life. But in about half of astronauts tested during and after spaceflight, Epstein-Barr virus reactivates. The same thing happens with other herpes viruses like varicella zoster, which causes chickenpox and shingles. Astronauts who haven't had a cold sore in decades suddenly develop them in space. Some experience shingles outbreaks, which can be excruciatingly painful. This viral reactivation is a warning sign. It tells us that something fundamental is going wrong with the immune system's ability to keep latent infections under control. And if the immune system is struggling with viruses that were already in the body, how well can it defend against new infections? On the International Space Station, if someone gets sick, they're only a few hours away from Earth. Medical evacuation is possible, even if it's complicated and expensive. On Mars, the closest hospital is 33 million miles away at the very minimum, and often as far as 250 million miles when Earth and Mars are on opposite sides of the Sun. Travel time would be measured in months, not hours. A simple infection that would be minor on Earth could become life-threatening on Mars. A urinary tract infection could progress to sepsis. A small cut could become dangerously infected. Even dental problems, something as simple as a tooth abscess, could turn into a medical emergency without the ability to perform proper dental surgery. And here's the kicker. Radiation makes all of this worse. Much worse. The cells of your immune system are among the most sensitive to radiation damage. They divide frequently, and rapidly dividing cells are particularly vulnerable to radiation-induced DNA damage. When your bone marrow, where most immune cells are produced, is exposed to chronic radiation, it becomes less efficient at generating new white blood cells. Studies conducted after the Chernobyl disaster and on atomic bomb survivors showed that radiation exposure suppresses immune function in a dose-dependent manner. The more radiation you receive, the more compromised your immune system becomes. And we're talking about Mars astronauts receiving doses that, while not immediately lethal, are still substantial enough to cause measurable immune suppression. Imagine being 9 months into the journey to Mars with a weakened immune system, living in an enclosed spacecraft where you can't escape your crewmates. If one person gets sick, the illness could rapidly spread through the entire crew. In the confined environment of a spacecraft, disease transmission is incredibly efficient. There's recycled air, shared surfaces, and no ability to truly isolate someone who's contagious. NASA has protocols for this, of course. Astronauts receive extensive medical screening before launch. They're quarantined for weeks to ensure they're not carrying active infections. Spacecraft are designed with medical supplies and equipment to handle common illnesses, but there's only so much that can be done with limited resources millions of miles from Earth. Let's shift gears and talk about something equally disturbing: what's happening inside the cells themselves at the molecular level. Every cell in your body contains about 6 billion base pairs of DNA, the genetic instructions that make you who you are. This DNA is constantly under attack from normal metabolic processes. Every day, each of your cells experiences tens of thousands of DNA lesions from oxidative stress, replication errors, and other routine cellular activities. Fortunately, your cells have repair mechanisms that fix almost all of this damage before it causes problems. But cosmic radiation creates a different kind of damage, one that's much harder to repair. When a high-energy heavy ion tears through a cell nucleus, it doesn't just break DNA in one place. It creates clusters of damage, multiple breaks and lesions in close proximity. Your cellular repair machinery struggles with these complex lesions. Sometimes the repairs are incorrect, leading to mutations. Sometimes the cell gives up and triggers apoptosis, programmed cell death. In tissues that regenerate frequently, like your skin or intestinal lining, this cell death might be manageable. Dead cells get replaced by new ones. But in tissues that don't regenerate well, like neurons in your brain or cardiac muscle cells, the loss of cells is permanent. Over the course of a 3-year Mars mission, the cumulative cellular damage would be substantial. Some scientists estimate that a significant percentage of neurons in critical brain regions could be damaged or destroyed by radiation exposure. This might not cause obvious, immediate symptoms, but it could manifest as subtle cognitive decline, slower reaction times, memory problems, difficulty with complex problem solving. Now imagine you're landing on Mars after experiencing this cognitive decline. You need to operate complex machinery, make critical decisions, and respond quickly to unexpected situations. But your brain isn't working quite as well as it did when you left Earth. The margins for error on Mars are razor thin. A small mistake could cascade into disaster. There's also the issue of cancer, though interestingly, it's not the most immediate concern for the mission itself. Cancer typically takes years or decades to develop after radiation exposure. The astronauts might complete their Mars mission and return to Earth seemingly healthy, only to develop leukemia or solid tumors 10 or 20 years later. NASA's current exposure limits are designed to keep the increased lifetime cancer risk below 3%. That might sound acceptable, but think about what it means. If you send a crew of 6 astronauts to Mars, statistically, you're sentencing at least one of them to eventually die from radiation-induced cancer. They're essentially trading years of their life expectancy for the opportunity to explore another planet. Is that an acceptable trade? That's not a question science can answer. It's a question of values, ethics, and what we as a society believe is worthwhile. But here's something that keeps scientists awake at night. All of our risk estimates are based on imperfect data. We've studied atomic bomb survivors, radiation workers, and cancer patients who received radiation therapy. We've irradiated animals in laboratories. We've collected data from astronauts on the space station. But we've never sent humans on a multi-year journey through deep space. Galactic cosmic rays are fundamentally different from the types of radiation we can study easily on Earth. They're more energetic, they include heavy ions that are rare in terrestrial settings, and the exposure is chronic rather than acute. Our risk models have to make assumptions and extrapolations that might not be accurate. What if the cancer risk is actually higher than we've estimated? What if there are synergistic effects between radiation and other spaceflight stressors that we haven't accounted for? What if long-term exposure to galactic cosmic rays causes health problems we haven't even thought to look for yet? These uncertainties are why some scientists argue that we shouldn't send humans to Mars until we have better shielding technology or faster propulsion systems. The unknowns are simply too great, and the potential for tragedy is too high. But others counter that we'll never have perfect knowledge. There will always be unknowns. At some point, if we want to become a spacefaring species, we have to accept calculated risks and move forward. The question is whether we've calculated those risks accurately enough. and whether the people taking them truly understand what they're signing up for. Now let's venture into territory that might be the most unsettling aspect of this entire discussion. What happens to the human mind during a 3-year journey to another planet? Because while radiation is silently damaging cells and bones are quietly dissolving, there's another threat that could undermine the entire mission: the psychological toll of isolation, confinement, and the sheer magnitude of what these astronauts are attempting. You need to understand something fundamental about human psychology. We evolved as social creatures, living in groups, with access to nature, variety in our environment, and the ability to escape from situations that stress us. A Mars mission violates every single one of these evolutionary adaptations. Picture yourself in a space roughly the size of a small RV. That's your entire world for 9 months. You're sharing this cramped environment with 5 or 6 other people. You can't go outside. Outside is instant death. You can't open a window for fresh air. You can't take a walk to clear your head. You can't call a friend who isn't already trapped in there with you. And everyone around you is dealing with the same stress, the same confinement, the same knowledge that if anything goes seriously wrong, you're all going to die together millions of miles from home. The psychological term for this is ICE, isolated, confined, and extreme environment. And humanity has some experience with ICE environments, though nothing quite like a Mars mission. Antarctic research stations, submarines, and analog missions here on Earth have given us glimpses into what happens to the human psyche under these conditions. The results aren't encouraging. One of the most comprehensive studies was conducted by the Russian Space Agency in collaboration with international partners. It was called Mars 500, and it took place from 2010 to 2011. 6 volunteers entered a sealed facility in Moscow and spent 520 days simulating a mission to Mars. The journey there, surface operations, and the return trip. Researchers monitored everything: sleep patterns, hormone levels, mood, cognitive performance, social interactions. They wanted to understand how isolation and confinement affected crew dynamics and individual psychology. What they found was fascinating and deeply troubling. As the mission progressed, crew members became increasingly sedentary. Their physical activity levels dropped dramatically, even though they had exercise equipment available. Sleep patterns became irregular and disrupted. Some crew members developed something researchers called temporal disintegration. They lost track of time, with their internal clocks drifting away from the 24-hour day-night cycle. Cognitive performance declined, particularly on tasks requiring sustained attention and complex problem-solving. Reaction times slowed. The crew made more errors on routine tasks. And perhaps most concerning, social cohesion began to fracture. Crew members withdrew from each other, spending more time alone in their quarters. Minor irritations escalated into interpersonal conflicts. Now, Mars 500 was conducted on Earth. The crew knew that if a true emergency occurred, they could leave. There was no real danger, no actual radiation exposure, no genuine risk of death. And yet, even under these relatively benign conditions, psychological and behavioral problems emerged. What happens when the stress is real? When there's no escape hatch? When crew members know that any serious conflict could jeopardize not just relationships, but survival itself? History provides some cautionary tales. Soviet and Russian space stations have experienced crew conflicts serious enough to compromise missions. American astronauts have reported tensions that made the confined environment nearly unbearable. In 1973, the crew of Skylab 4 went on what's been called a strike in space, shutting off communications with mission control for a day because they were overwhelmed and exhausted. And these were missions lasting weeks or months, with Earth visible outside the window, a constant reminder that home was just a few hours away. On a Mars mission, there will come a point, about 3 months in, when Earth is just another bright star in the sky. You won't be able to see continents or clouds or any reminder that it's a living world. The psychological impact of that disconnection is difficult to overstate. There's also the communication delay. Initially, radio signals between Earth and the spacecraft might take only a few minutes to travel each way. But as the distance grows, that delay stretches to 20 minutes or more. You can't have a real-time conversation. You send a message, then wait 40 minutes for a response. This time lag makes it nearly impossible to receive meaningful emotional support from loved ones back home. Imagine you're having a terrible day. You're stressed, scared, maybe experiencing a panic attack. You desperately want to talk to your spouse or your best friend, so you send a message. Then you wait. 20 minutes pass while your message travels through space. They receive it, process it, record a response. Another 20 minutes for their reply to reach you. By the time you hear their voice, nearly an hour has passed, and you're in a completely different emotional state. The comfort that real-time connection provides is simply unavailable. This communication isolation creates a unique form of loneliness that Earth-bound analogs can't fully replicate. You're psychologically on your own in a way that no Antarctic explorer or submarine crew has ever experienced. Even astronauts on the International Space Station can have real-time conversations with family and mission control. And then there's the boredom. People often underestimate how psychologically damaging monotony can be. Yes, there will be work to do, maintaining systems, conducting experiments, preparing for Mars arrival, but much of this work will be routine. Day after day, the same tasks in the same environment with the same people. Humans need novelty. Our brains crave new experiences, new sights, new challenges. In space, there's virtually nothing new. You see the same walls every day. You eat the same freeze-dried food. You follow the same schedule. The view outside is an unchanging field of stars. This sensory deprivation can lead to a condition called stimulus hunger, where people become desperate for any form of new input. Some crew members might cope by withdrawing into themselves, which can damage team cohesion. Others might become irritable or develop obsessive behaviors. In extreme cases, sensory deprivation can even lead to hallucinations or dissociative episodes. NASA is acutely aware of these psychological risks. They've invested heavily in crew selection, choosing astronauts who demonstrate exceptional psychological resilience. They've developed training programs focused on team building, conflict resolution, and stress management. Mission designs include provisions for private space, virtual reality systems to provide simulated nature experiences, and carefully planned schedules that include leisure time and celebrations of holidays and personal milestones. But here's the thing that makes all of this exponentially more difficult. Radiation doesn't just damage your body, it damages your brain, and specifically the regions responsible for emotional regulation and stress response. Remember those heavy ions we discussed earlier, the ones tearing through tissue at nearly the speed of light? When they strike the brain, they don't discriminate. They damage neurons in the hippocampus, which is critical for memory formation. They affect the prefrontal cortex, which handles executive function and decision-making. And crucially, they impact the amygdala and other structures involved in emotional regulation and anxiety response. Animal studies have shown that radiation exposure similar to what astronauts would experience on a Mars mission leads to increased anxiety-like behaviors, impaired fear extinction, meaning subjects have trouble letting go of fearful memories, and reduced social interaction. In some experiments, irradiated mice showed signs of what in humans we would call depression or anhedonia, the inability to experience pleasure. Now imagine you're already dealing with the psychological stress of isolation and confinement. You're millions of miles from Earth in a tiny spacecraft. And on top of that, the radiation you're being exposed to is literally changing your brain chemistry in ways that make you more anxious, more prone to depression, and less capable of managing stress. It's a vicious cycle. The environment creates psychological stress, and the radiation makes you less capable of coping with that stress, which increases the psychological burden, which might lead to behaviors like exercising less or sleeping poorly that make the physical effects of radiation even worse. Scientists call this the behavioral health and performance risk, and it's one of the most difficult to quantify and mitigate because it involves complex interactions between biology, psychology, and social dynamics. You can't just throw more shielding at the problem or design better exercise equipment. You're dealing with the fundamental question of whether human beings are psychologically equipped for this kind of journey. Some researchers have proposed pharmaceutical interventions, medications that could help stabilize mood or enhance resilience. But that opens another can of worms. How do psychiatric medications interact with radiation exposure? How effective are they in altered gravity? What happens if someone develops medication dependency or adverse reactions when you're months away from any possibility of medical consultation with specialists on Earth? There's also the question of autonomy. As the communication delay increases, the crew will need to become increasingly independent from mission control. On the Moon, astronauts could receive real-time guidance from Earth. On Mars, that's impossible. The crew will need to make critical decisions on their own, sometimes with minutes to respond to emergencies. This autonomy is psychologically double-edged. On one hand, it can be empowering. The crew becomes masters of their own fate, capable and confident. On the other hand, it places enormous responsibility on individuals who might be cognitively impaired from radiation exposure and psychologically strained from months of isolation. What happens when a crew member's judgment is compromised, but they're the ones who need to make a life-or-death decision? Do the other crew members recognize the impairment and override their colleague? How do you handle that conflict in an environment where every relationship is critical to survival? Let me share something that perfectly illustrates how precarious this psychological balance can be. In the late 1990s, a Russian cosmonaut aboard the Mir space station became so frustrated with malfunctioning equipment that he disconnected a computer cable, nearly causing catastrophic systems failures. His colleagues had to physically restrain him and reconnect the cable to prevent disaster. This happened after just a few months in space, on a station in low Earth orbit where rescue was possible within hours. What happens after 9 months in deep space when someone reaches their psychological breaking point? NASA has developed psychological support protocols, including regular video conferences with psychiatrists and psychologists on Earth. But remember that communication delay. By the time a crisis is recognized on Earth and a response is formulated and transmitted, the situation could have already escalated beyond control. Some mission architectures include trained medical personnel in the crew, someone with psychiatric training who can provide immediate support. But that person is also dealing with the same stressors as everyone else. They're not an objective outside observer. They're living in the same pressure cooker, experiencing the same radiation exposure, facing the same dangers. And here's something most people don't consider. The crew will be carefully selected for psychological compatibility, but that selection process is based on behavior observed on Earth. There's emerging evidence that space itself changes personality in ways we don't fully understand. Astronauts on the International Space Station have reported a phenomenon called the overview effect, a profound cognitive shift that occurs when you see Earth from space. The planet appears as a fragile blue marble suspended in an infinite void. Political boundaries disappear. Human conflicts seem absurd. Many astronauts describe it as a deeply spiritual or philosophical experience that fundamentally changes their perspective on life. For most, this is positive. But what happens when you're so far from Earth that you can't even see it as a marble anymore? What happens when you look back and Earth is just another point of light, indistinguishable from countless other stars? Does that distance create a sense of freedom and possibility, or does it trigger existential dread and feelings of cosmic insignificance? Different people might react in dramatically different ways, and we won't know until we actually send humans on that journey. The psychological screening and training can only go so far. We're venturing into truly uncharted territory in terms of human psychology. There's also the question of what scientists call third-quarter phenomenon. Studies of people in isolated environments, Antarctic stations, long submarine deployments, have identified a pattern. The first part of the mission is characterized by excitement and novelty. The middle section settles into routine. But then, roughly 3/4 of the way through, there's often a psychological crisis. People become acutely aware of how much time has passed and how much still remains. The end is visible but not yet close. This is when depression, interpersonal conflicts, and behavioral problems tend to spike. For a Mars mission, the third quarter would fall somewhere during the surface operations or early return journey, exactly when crew performance needs to be at its peak. Imagine dealing with the third quarter phenomenon while simultaneously trying to conduct complex scientific experiments, maintain life support systems, and prepare for the dangerous journey home. Add radiation-induced cognitive impairment and months of cumulative stress, and you have a recipe for catastrophic performance failures. Now let's zoom out and consider the bigger picture, the ethical dimensions of what we're discussing. NASA is not hiding these risks. The agency publishes extensive documentation about the hazards of deep space exploration. Scientists present their findings at conferences and in peer-reviewed journals. The information is publicly available for anyone who wants to look for it. But there's a difference between technical documentation and public awareness. Most people, when they think about Mars missions, imagine the excitement of landing on another planet. They picture astronauts planting flags and collecting samples. They don't picture the 9 months of psychological torment and cellular destruction that precedes that moment. They don't consider the decades of increased cancer risk that follows. When NASA eventually recruits the crew for the first Mars mission, those individuals will be briefed extensively on the risks. They'll sign informed consent documents. They'll know what they're getting into, at least intellectually. But can anyone truly comprehend what it will be like until they're actually living it? There's a concept in bioethics called therapeutic misconception, the tendency for research participants to underestimate risks and overestimate benefits, especially when they're motivated by the possibility of being part of something historic. Will Mars astronauts fall victim to therapeutic misconception? Will they convince themselves the risks are manageable because they want so badly to go? And what about the rest of us? Society will be watching. We'll celebrate the launch. We'll follow the mission on social media. If something goes wrong, if an astronaut develops acute radiation sickness or a psychological crisis leads to tragedy, how will we reconcile our collective excitement with the human cost? Let's talk about something that ties all of these dangers together in a way that's particularly insidious: the problem of synergistic effects. In medicine and biology, synergy occurs when 2 or more factors interact to produce an effect greater than the sum of their individual effects. 1 plus 1 doesn't equal 2, it equals 3 or 4 or 10, and that's exactly what we're facing with Mars missions. Radiation, microgravity, isolation, confinement, distance from Earth. Each of these hazards is dangerous on its own, but when they occur simultaneously over a 3-year period, they amplify each other in ways that are difficult to predict and even harder to prevent. Here's a concrete example. We know that radiation damages the cardiovascular system. We also know that microgravity causes cardiovascular deconditioning. Your heart becomes weaker, your blood volume decreases. When these 2 factors combine, the damage to the cardiovascular system is likely worse than either factor alone would produce. But it doesn't stop there. Cardiovascular problems reduce exercise capacity. If astronauts can't exercise as effectively, they lose more bone and muscle mass. Increased bone loss means more calcium is released into the bloodstream, which can lead to kidney stones, an excruciatingly painful condition that would be a medical emergency on Mars. Muscle atrophy makes it harder to perform physically demanding tasks, increasing stress levels. Elevated stress impairs immune function and sleep quality. Poor sleep amplifies cognitive impairment from radiation exposure. Cognitive impairment leads to errors and poor decision-making, which increases mission risk and crew anxiety, creating more stress. Do you see the spiral? Each problem feeds into another, creating cascading failures across multiple body systems. Scientists call this allostatic load, the cumulative burden of chronic stress and physiological dysregulation. When allostatic load becomes too high, systems start breaking down in ways that are difficult to reverse. NASA has sophisticated computer models that attempt to predict these interactions, but models are only as good as the data that informs them. And we simply don't have data on what happens to humans during 3-year missions in deep space. The longest anyone has spent in space is 437 days. Russian cosmonaut Valery Polyakov's record-setting mission aboard Mir in 1994 to 1995. Polyakov's mission provided valuable data, but it was in low Earth orbit, still partially protected by Earth's magnetic field. The radiation exposure was a fraction of what a Mars crew would experience. And it was one person, one data point. We can't build reliable models on single data points, especially when individual variability is so significant. Some people tolerate radiation better than others due to genetic differences in DNA repair mechanisms. Some people are psychologically more resilient to isolation. Some maintain bone density better in microgravity, but we don't fully understand why these differences exist or how to predict who will fare better on a Mars mission. This brings us to one of the most ethically fraught aspects of mission planning: crew selection. How do you choose 6 humans to send on a journey where the risks are known to be severe, but the exact outcomes are unpredictable? Do you select younger astronauts who have more years of life ahead of them, but will carry the radiation burden for decades? Or older astronauts who are more experienced, but might be more vulnerable to radiation-induced health effects? Do you consider genetic screening to identify individuals with superior DNA repair capabilities? If so, does that constitute genetic discrimination? What about gender? Studies have shown that women are generally more susceptible to radiation-induced cancer than men, particularly breast and ovarian cancer. Does that mean Mars crews should be all male? But women tend to have better psychological resilience in isolated environments and often demonstrate superior teamwork and communication skills. How do you balance these factors? These aren't just abstract ethical questions. They're practical decisions that mission planners will need to make, and whatever choices they make will be scrutinized, debated, and potentially criticized by the public, ethicists, and future historians. Let's shift perspective for a moment and consider what all of this looks like from the astronaut's point of view. Not the technical risks and statistics, but the lived experience of confronting these dangers day after day. You wake up in your sleeping quarters, a space roughly the size of a phone booth. Your back aches from months of microgravity, despite the exercise regime you follow religiously. You check your radiation dosimeter, the device that tracks your cumulative exposure, and see that you've already received more radiation than most people on Earth will experience in a lifetime. And you're not even halfway to Mars yet. You float to the communal area where your crewmates are already awake. Someone is having trouble with the waste management system again, a euphemism for the toilet. It's the third malfunction this week. Everything smells vaguely of sweat and recycled air, despite the sophisticated filtration systems. You haven't experienced a natural scent, fresh air, rain, grass, in 7 months. You're beginning to forget what they smell like. Breakfast is a pouch of rehydrated scrambled eggs and a nutrient bar. You've been eating variants of this meal for so long that you've lost the ability to taste the subtle differences between them. Everything tastes like cardboard. Your appetite has diminished anyway, a common effect of long-duration spaceflight that scientists still don't fully understand. After breakfast, you begin your work shift. Today you're conducting a routine maintenance check on the life support systems. These systems are literally keeping you alive, generating oxygen, removing carbon dioxide, recycling water from urine and sweat. If they fail, you have perhaps hours before the air becomes unbreathable. No pressure, right? As you work, you notice your hands trembling slightly. Is it fatigue, anxiety, or is it something worse? Early signs of radiation-induced neurological damage? You've been having trouble remembering procedures lately, needing to check the manual for tasks you used to do from memory. Your crewmates have noticed too, though nobody says anything directly. Everyone is dealing with similar symptoms, and acknowledging them would only increase the collective anxiety. Midday, you have a scheduled video call with your family. You recorded a message yesterday, asking how everyone is doing, sharing some anecdotes from the mission. Today, you'll receive their response, recorded 48 hours ago. Your daughter's birthday was last week. You missed it. You sent her a recorded message, of course, but she received it 3 days after the actual celebration. By the time you see video of her blowing out the candles, the cake will have been eaten, the decorations taken down, the moment long past. This asynchronous existence is profoundly disorienting. You're living in everyone else's past, and they're living in yours. There's no shared present moment. It's like being a ghost, observing life on Earth, but not truly participating in it. In the afternoon, a solar radiation alert comes through. A coronal mass ejection erupted from the sun 2 days ago, and the radiation wave is approaching your spacecraft. You and your crewmates retreat to the storm shelter, a small compartment in the center of the spacecraft, surrounded by water tanks and equipment that provides some additional shielding. You spend the next 30 hours in this space, which is barely large enough for 6 people to sit comfortably. There's nothing to do but wait. You try to sleep, but anxiety makes it difficult. You know the shelter only reduces your radiation exposure. It doesn't eliminate it. Right now, high-energy particles are passing through the walls, through the water, through your body. Some of them are hitting DNA strands, creating damage that your cells may or may not be able to repair correctly. When the all-clear finally comes, you emerge stiff and exhausted. You check your dosimeter. The storm added another 30 millisieverts to your cumulative dose. You're now at levels that would disqualify you from ever returning to space after this mission, assuming you make it home. Your career as an astronaut will effectively be over, not because you failed, but because your body has absorbed too much radiation to safely go back. The psychological weight of that realization settles over you. This is it. Your one and only deep space mission. You'll never see the view from Mars' orbit again. You'll never experience the profound silence of interplanetary space. And if the radiation has damaged your body in ways that manifest years from now, heart disease, cancer, neurological problems, you might not even have many years left to appreciate having survived. But you push these thoughts aside because dwelling on them serves no purpose. You focus on the mission. There's always something that needs attention: a malfunctioning sensor, a software glitch, a science experiment requiring data collection. The work provides structure and meaning, a psychological anchor in an environment that often feels surreal and dreamlike. As the months continue, you notice changes in your crewmates. The pilot, who was always energetic and talkative, has become withdrawn. She spends more time alone in her quarters, participating in group activities only when absolutely necessary. The mission commander tries to draw her out, but she insists she's fine, just tired. Everyone is tired. Exhaustion has become the baseline state of existence. The medical officer reports that everyone's bone density scans show significant deterioration. He's particularly worried about 2 crew members whose losses exceed even the pessimistic predictions. They'll need aggressive treatment when they return to Earth: bisphosphonate drugs, intensive physical therapy, possibly even surgical interventions. That's assuming the bones don't fracture before then. One night, though night and day have lost most of their meaning in the perpetual artificial lighting of the spacecraft, you experience something that will stay with you forever. You're floating near one of the small observation windows, looking out at the stars. Earth is no longer visible as a disk. It's just a pale blue point of light, easily lost among thousands of other stars. And suddenly, the full magnitude of your isolation hits you. You're 40 million miles from every human being who has ever lived, except for the 5 people in this metal container with you. If you died right now, your body couldn't be buried on Earth. You'd either be stored in the spacecraft for the remainder of the mission, an impossible psychological burden for your crewmates, or you'd be cremated or committed to space, your atoms joining the cosmic dust between planets. Your species evolved in the rift valleys of Africa. Your ancestors migrated across continents, yes, but always on the surface of one planet, always breathing Earth's atmosphere, always held by Earth's gravity. You are doing something no human has ever done, pushing the boundaries of where our species can exist. And the cost of that achievement is measured in bone density lost, in neurons damaged, in years of life potentially shortened. Is it worth it? In this moment of profound isolation and fear, you genuinely don't know. But you're committed now. There's no turning back. Mars awaits. Eventually, after 9 months that feel simultaneously like 9 years and 9 days, Mars begins to resolve into more than just a bright reddish star. You can see it as a disk, then as a world with visible features. The massive volcanic peaks of Tharsis rise from the surface. The colossal canyon system of Valles Marineris cuts across the equator like a scar. The polar ice caps gleam white against the rust-colored terrain. Despite everything, the exhaustion, the physical deterioration, the psychological strain, excitement builds among the crew. This is what you came for. This is the moment that will justify all the sacrifice and suffering. You're about to become one of the first humans to set foot on another planet. But that excitement is tempered by new anxieties. The landing will be dangerous. Your spacecraft is going to enter the Martian atmosphere at over 12,000 miles per hour. You'll experience forces up to 8 times Earth's gravity during deceleration. Remember that your cardiovascular system has been weakened by 9 months of microgravity. Your heart might struggle to pump blood against those G-forces. There's a real risk of blackouts or even heart failure during the descent. And your bones, those fragile calcium-depleted structures that used to support your weight on Earth, will suddenly need to bear weight again. Mars' gravity is only 38% of Earth's, but after 9 months of complete weightlessness, even that might be too much. You've been doing resistance exercises throughout the journey, but everyone knows it's not enough. Will you be able to walk when you land, or will you collapse under even the modest pull of Martian gravity? The landing sequence is harrowing. The spacecraft shudders and groans as it slams into the thin Martian atmosphere. The heat shield glows cherry red, and the interior temperature rises despite the insulation. G-forces build, pressing you into your seat with crushing weight. Your vision narrows to a tunnel. You focus on breathing, on staying conscious, on trusting that the spacecraft will do what it's designed to do. And then, miraculously, you're down. The engines shut off. The violent shaking stops. For the first time in 9 months, you feel weight. It's gentle compared to Earth, but after months of floating, it feels profound. Your body sags into the seat. Your arms, held out in front of you, fall to your lap. You have mass again. You have up and down. The crew sits in stunned silence for a moment, processing the fact that you've survived. Then someone starts laughing, a slightly hysterical sound that's equal parts relief and disbelief. Others join in. You've made it. Against all odds, through all the dangers, you've reached Mars. But the celebration is brief, because reality quickly sets in. You try to stand and immediately understand the severity of your physical deterioration. Your legs shake. Your muscles, atrophied from months of disuse, scream in protest at being asked to support even your reduced weight. You manage a few steps, but they're lurching and unsteady, like a toddler learning to walk. Everyone is experiencing similar difficulties. The mission commander, who is a marathon runner on Earth, needs assistance moving from her seat to the hatch. The medical officer's face is pale and drawn, and he's sweating from the exertion of simply standing. This is going to make the already difficult work of establishing the Mars habitat even more challenging. Over the next few days, you begin adapting to Martian gravity. Your muscles gradually remember how to work against weight. You can walk without assistance, though you tire quickly, and everything takes longer than it should. The physical work of deploying equipment, setting up solar panels, and connecting habitat modules is exhausting in ways you didn't anticipate. And through all of this, you're still being bombarded by radiation. Mars has no magnetic field and only a thin atmosphere, providing minimal protection from galactic cosmic rays. The radiation environment on the surface is actually worse than it was in space, because now you're also being exposed to secondary particles created when cosmic rays strike the Martian soil. Your habitat has some shielding, walls made of composite materials, and plans to eventually cover the structure with Martian regolith for additional protection. But construction is slow, and in the meantime, you're receiving significant radiation doses every single day. Your cumulative exposure is approaching levels that would have been considered unacceptable for any mission just a generation ago. But here you are, because the alternative is not going to Mars at all. The work continues. You conduct geological surveys, collect samples, deploy scientific instruments. The science is fascinating. Evidence of ancient water flows, potential biosignatures in certain rock layers, data that will keep researchers on Earth busy for decades. This is what you came for. This is humanity's foothold on another world, but it's also relentlessly difficult. Everything is harder on Mars. The spacesuits are bulky and restrictive. The temperature swings are extreme, relatively warm in the afternoon sun, plummeting to -80 degrees Celsius at night. Dust gets into everything, despite your best efforts to keep it out of the habitat. The Martian soil is full of perchlorates, toxic chemicals that make it unsuitable for growing plants without extensive processing. And you're still isolated, still millions of miles from Earth. The communication delay is now between 4 and 24 minutes one way, depending on the orbital positions of the two planets. You send reports to mission control and wait. You receive instructions and implement them hours after they were sent, hoping the situation hasn't changed in the meantime. The psychological challenges don't ease on Mars. In some ways, they intensify. You thought arriving would provide relief, a sense of accomplishment that would sustain morale. And it does, initially. But after a few weeks, the novelty wears off and you're left with the reality. You're living in a tiny habitat on a dead world, breathing recycled air, eating prepackaged food, performing exhausting physical labor every day while your body continues to deteriorate. The landscape, while scientifically fascinating, is also profoundly desolate. There's no life here. No movement except the wind stirring dust. No sound except the hum of habitat systems and the muffled voices of your crewmates. Earth has birdsong, rustling leaves, rainfall, ocean waves, a symphony of natural sounds that you never appreciated until they were gone. Mars is silent in a way that Earth never is, and that silence becomes oppressive. You find yourself thinking about home constantly. Not home as in the house you lived in before the mission, but Earth itself. You dream about walking through a forest, feeling rain on your face, breathing air that hasn't been recycled through scrubbers 1,000 times. You'd give almost anything for a piece of fresh fruit, an apple, a strawberry, anything that wasn't freeze-dried or vacuum-sealed months or years ago. The crew's dynamics continue to shift in subtle and not-so-subtle ways. The pilot who became withdrawn during the journey has developed what the medical officer quietly acknowledges might be clinical depression. She fulfills her duties, but there's a mechanical quality to her actions, as if she's going through motions without truly being present. The medical officer has limited pharmaceutical options. Antidepressants were included in the medical supplies, but their effectiveness in the Mars environment is uncertain, and there are concerns about interactions with radiation exposure. 2 other crew members have developed a romantic relationship, which wasn't anticipated or planned for, but perhaps was inevitable. 6 people, isolated for years, with no one else for companionship or intimacy. NASA's official policies on this are deliberately vague, recognizing that adult humans will make their own choices, but it adds complexity to group dynamics. The other 4 crew members now feel like outsiders to this partnership, creating a subtle division within the team. And then there's the medical officer's discovery that changes everything. During a routine health check, he finds something concerning in his own blood work, abnormal cell counts that might indicate early-stage leukemia. It could be a false alarm, a temporary fluctuation caused by the extreme environment, or it could be radiation-induced cancer manifesting far earlier than anyone predicted. There's no way to know for certain with the limited diagnostic equipment available on Mars. He needs a bone marrow biopsy, advanced imaging, consultations with oncologists on Earth. But Earth is currently 150 million miles away, and the communications delay means any consultation would be fragmented and frustrating. Even if the diagnosis is confirmed, treatment options are virtually non-existent. The habitat doesn't have chemotherapy drugs or the facilities to administer them safely. The medical officer faces an impossible decision. Does he tell the crew immediately, potentially devastating morale at a critical phase of the mission? Does he wait, monitor his symptoms, and hope it's nothing serious? Does he inform mission control and wait nearly an hour for their guidance to arrive? He chooses to tell the commander first in private. Together they decide to inform the full crew, but present it as preliminary findings requiring monitoring, concerning but not immediately alarming. They emphasize that it might be nothing, that they'll continue gathering data, but everyone understands the subtext. One of you might be dying, and there's nothing anyone can do about it. This revelation casts a shadow over the remaining surface operations. The mission continues because it must. There are experiments to conduct, samples to collect, data to gather. But the psychological burden has increased dramatically. You're all acutely aware that the dangers you accepted intellectually before launch have become horrifyingly concrete. Radiation isn't just an abstract risk anymore. It's potentially killing your crewmate, and any of you could be next. The 18-month surface stay, which already felt long, now seems interminable. Every day is a countdown to departure, to beginning the 9-month journey home. But departure brings its own anxieties. The medical officer's condition might worsen during the return trip. What happens if he requires care beyond what the crew can provide? What if someone else develops similar symptoms? And there's a darker question that nobody voices but everyone thinks about. What happens if someone becomes so sick that their survival is impossible, and their continued existence consumes resources the rest of the crew needs? In the most extreme scenario, would difficult decisions about resource allocation need to be made? These are ethical dilemmas that mission planners have considered in confidential documents, hoping they'd never need to be implemented. Finally, departure day arrives. You take one last look at the habitat that's been your home, at the reddish landscape you've come to know intimately. Part of you is relieved to be leaving, to be one step closer to Earth, to medical facilities, to breathable air and open skies. But another part feels a strange reluctance. You've accomplished something extraordinary here. You've expanded human presence to another world. Leaving feels like abandoning that achievement. The ascent from Mars is smoother than the landing, though still stressful. You reach orbit successfully and dock with the return vehicle that's been waiting in Martian orbit since before you arrived. This spacecraft will be your home for the next 9 months as you cross the void back to Earth. If the journey to Mars was difficult, the return is exponentially worse. You're more damaged now, physically weaker, carrying a greater radiation burden, psychologically exhausted. The novelty that sustained you during the outbound journey is gone. There's no exciting destination ahead, just the long, slow crawl back across millions of miles of empty space. The medical officer's condition deteriorates. His cell counts become increasingly abnormal. He develops fatigue, night sweats, and unexplained bruising, classic signs of advancing leukemia. The crew watches helplessly as he weakens, administering palliative care with their limited resources, but unable to provide the treatment he desperately needs. 4 months into the return journey, he becomes too weak to leave his sleeping quarters. The crew takes turns sitting with him, providing comfort, helping with basic needs. Mission Control sends messages of support and guidance for managing his symptoms, but everyone knows how this ends. He's dying, and you're all witnesses to it, trapped in this spacecraft with no escape. When he finally passes, 5 months into the return journey, the grief is overwhelming and complicated. You've lost a colleague, a friend, someone you've lived with in intimate proximity for over 2 years. But there's also relief. Relief that his suffering has ended, and perhaps guiltily, relief that the psychological burden of watching him decline is over. His body is stored in the coldest section of the spacecraft, preserved as well as possible for return to Earth. The crew holds a memorial service, sharing memories and acknowledging his sacrifice. But the presence of his body, the physical reminder of mortality and the mission's cost, weighs on everyone for the remaining 4 months of the journey. You arrive back at Earth orbit, diminished in every way. You've lost significant bone density and muscle mass. Your cardiovascular system is compromised. You've accumulated radiation exposure that will increase your cancer risk for the rest of your life, which might itself be shortened by years or decades. You've watched a crewmate die from radiation-induced illness. You carry psychological scars from 3 years of isolation, confinement, and constant awareness of danger. The medical team that examines you upon return is shocked by the extent of the physical damage. You'll spend months in rehabilitation, relearning how to function in Earth's gravity. Some of the bone loss might be permanent. The radiation damage is irreversible. You'll need regular cancer screenings for the rest of your life, always wondering when the accumulated damage might manifest as disease. But you did it. You went to Mars. You're one of the first humans to set foot on another planet. Your name will be in history books. Children centuries from now will learn about your journey. The samples you collected, the data you gathered, the experiments you conducted, they'll advance human knowledge in ways that ripple forward for generations. Was it worth it? That question haunts you during the long months of rehabilitation. Physical therapists guide you through exercises to rebuild muscle and bone. Psychologists help you process the trauma of what you experienced. You do interviews, give presentations, write a memoir that becomes an international bestseller. The public celebrates you as a hero, an explorer, a pioneer. But late at night when you're alone with your thoughts, you remember the reality, the fear, the pain, the relentless accumulation of damage to your body, the image of your crewmate's body stored in the cold section of the spacecraft for 4 months, the knowledge that your life expectancy has been shortened by years, perhaps decades. by radiation you couldn't escape, and you wonder about the next crew. Because there will be a next crew. NASA is already planning the second mission, incorporating lessons learned from your experience. They're developing better shielding, faster propulsion systems, improved medical capabilities. But the fundamental challenges remain. You can't escape radiation in deep space. You can't prevent bone loss in microgravity without artificial gravity, which remains technologically elusive. You can't eliminate the psychological toll of years-long isolation. The next crew will face the same dangers you faced. They'll know what they're getting into. Your mission provided the data that was lacking before. But will that knowledge make the experience easier or harder? Is it better to understand exactly what horrors await you, or to go into the unknown with optimistic naivety? 5 years after your return, you attend a medical checkup that changes everything. The oncologist finds abnormalities in your blood work. Further testing reveals thyroid cancer, almost certainly radiation-induced. It's early stage, treatable, and the prognosis is good, but you know this is just the beginning. The radiation damage you accumulated on Mars is a time bomb in your body, waiting to manifest as cancer, cardiovascular disease, or other conditions. You undergo surgery to remove the tumor. The operation is successful, but you're now on thyroid medication for life, and you'll need regular monitoring to watch for recurrence or additional cancers. 2 of your surviving crewmates have developed similar conditions. The pilot who struggled with depression on Mars never fully recovered psychologically and eventually took her own life, a tragedy that devastated the tight-knit community of Mars mission veterans. A decade after the mission, you're invited to speak at the launch of the 4th Mars expedition. Technology has advanced. The journey is now only 6 months each way instead of 9, thanks to more efficient propulsion. The spacecraft has better radiation shielding, cutting exposure by nearly 30%. The crew has access to artificial gravity through a rotating section of the spacecraft, which should reduce bone and muscle loss significantly. These improvements are real and meaningful, but they're incremental, not revolutionary. The astronauts preparing to launch still face profound dangers. They'll still accumulate radiation doses far beyond anything most humans experience. They'll still spend a year and a half isolated from Earth. They'll still risk their health and, potentially, their lives. You look at their eager faces during the pre-launch ceremony. They're younger than you were, filled with the same excitement and determination you felt before your own mission. They've studied your experiences. They know the risks, and they're going anyway because humans are explorers. It's fundamental to who we are as a species. In your speech, you're honest about the challenges. You don't sugarcoat the dangers or romanticize the experience. But you also talk about the profound meaning of expanding human presence beyond Earth. You describe the moment you first saw Mars resolved into a world, not just a point of light. You talk about the scientific discoveries, the technological advances that resulted from solving the mission's challenges, the inspiration it provided to millions of people on Earth. You tell them that despite everything, despite the physical damage, despite watching a crewmate die, despite the cancer diagnosis years later, you would make the same choice again, because some achievements justify their costs, because pushing the boundaries of human possibility matters, because our species' long-term survival might depend on becoming multiplanetary. But you also tell them to go into it with their eyes open, to understand that they're trading years of their lives, and possibly their lives themselves, for the opportunity to explore another world. That's a trade some people believe is worthwhile and others don't, and both positions are valid. The launch proceeds flawlessly. You watch the spacecraft climb into the sky on a pillar of fire, carrying 6 more humans toward Mars and all the dangers that await them there. You feel pride, anxiety, hope, and sorrow in equal measure. The question of whether we should send humans to Mars doesn't have a simple answer. The dangers are real, profound, and in some cases unavoidable given current technology. Radiation exposure alone poses risks that we can mitigate but not eliminate. The physical deterioration from long-duration spaceflight and reduced gravity is severe. The psychological challenges are immense. The medical risks are substantial, and the capacity to respond to medical emergencies is extremely limited. But humans have always pushed into dangerous frontiers. We crossed oceans in wooden ships. We climbed mountains that killed experienced climbers. We ventured to the poles of our planet in conditions that claimed many lives. Exploration has always been dangerous, and it has always been worth it to those who chose to go. The key is informed consent and honest communication. Astronauts need to truly understand the risks they're accepting, not just intellectually but viscerally. The public needs to understand that Mars missions will likely result in shortened lifespans, increased cancer rates, and possibly deaths. We need to decide as a society whether we're comfortable with that cost. And we need to keep working on the technology to make it safer. Faster propulsion to reduce journey time. Better shielding materials to reduce radiation exposure. Artificial gravity systems to prevent bone and muscle loss. Advanced medical capabilities for the spacecraft and Mars habitats. Pharmaceutical interventions to mitigate radiation damage at the cellular level. Some of these advances are on the horizon. Some are decades away. Some might not be achievable with current physics and engineering, but each improvement brings the risk down incrementally, making Mars missions safer for future crews. The dream of humans on Mars is not going away. Too many people have devoted their careers to making it happen. Too much has been invested, financially, politically, emotionally. Humans will go to Mars. The question is not if, but when, and at what cost. And when they go, they'll carry with them the hopes and dreams of everyone who looks up at that reddish point of light in the night sky and wonders what it would be like to stand on another world. They'll also carry the burden of very real dangers that will test the limits of human endurance and courage. The stars are calling us. They always have. But the path to reach them is paved with radiation, isolation, physical deterioration, and profound risk. That's the reality behind the dream. That's the price of becoming a spacefaring species. Whether it's a price worth paying, that's a question each generation will have to answer for itself. If you found this deep dive into the real dangers of Mars missions eye-opening, please give this video a thumbs up and subscribe to the channel. And if you're curious about why returning to the moon is presenting unexpected challenges, even though we've done it before, check out the video on the screen. Why going back to the moon is harder than going the first time. It's a must-watch.